time I start a new chapter for a functional group, you'll know the typical rhythm, right? We're going to talk about the properties, and then we'll talk about how those functional groups can be made, and then what we can do with those functional groups. So this chapter is really no difference. And although it encompasses a lot of functional groups, namely the acid halides, the carboxylic acids, esters, amides, and anhydrides, it seems daunting. Fear not, there's one mechanism. What I want to point out first is that what sets these apart from the ketone and aldehyde chapter that we just saw. Remember, ketones have carbons flanking both sides of the carbonyl, right? And a carbonyl is the carbon double bond oxygen. So notice every single one of these has a carbon double bond oxygen. They all have a carbonyl. An aldehyde has a carbon, typically, but definitely a hydrogen flanking one side. So the aldehyde and the ketone have something in common, and that's the fact that the two atoms flanking the carbonyl are pretty strong bonds, right? You think about our 1,2 additions, the two atoms that were originally flanking the functional group, those were not going to come off. Something else might come off, but those are definitely not going to come off. Why we end up grouping all of these carboxylic acid and their derivatives together is because the atom flanking the carbonyl is not a carbon or hydrogen. So if you look at every case, there could be a halogen or an OH or an OR or an NR2 or an NH2 or another oxygen where you can look at this whole thing. This whole thing is an ester. Every group off of the carbonyl is not a carbon or a hydrogen. Thus, every one of those groups is eligible to leave in an in, up, down, out mechanism. Okay, so that said, that's what we're going to end up seeing this chapter in an exhaustive fashion, I will say. So carboxylic acids, let's think about some properties of them. They are, so I've circled, we're going to focus on the carboxylic acid in particular. They are polar, right? They have a very strong dipole. And they are protic. That's what makes them acidic. They have a hydrogen right off of the oxygen. These systems, due to the hydrogen off of the oxygen, allow for hydrogen bonding dimers. So what happens here's one carboxylic acid. And if I draw another carboxylic acid, but upside down, you can see that all of their electronics align, right? The partially negative oxygen is attracted to the acidic proton of the carboxylic acid, and vice versa. So these dimers have 2 hydrogen bonding points. What do you think that says about hydrogen bond or the melting points given these hydrogen bonding trends and boiling points? What do you think? Are they going to be high or low relatively? Well, if you guessed high, you were correct. They tend to be higher in melting points and boiling points because of these very strong hydrogen bonding intermolecular forces. How about solubility in water? Well, if you guess soluble, in general, again, it depends on how many carbon chains, how greasy the system is, but in general, carboxylic acids allow for, or tend to allow for, the solubility of water. Like dissolves like, right? So it can hydrogen bond to water and thus give us a solution. As for naming, you guys all know I'm not huge in spending a ton of time in IUPAC naming, so here is the simplicity of it. The ending oic acid right? You've got one carbon, it's methanoic acid. You've got two carbons, you've got ethanoic acid. Three carbons, it's propanoic acid. That's about all I'm going to go into it. Oic acid indicates that you have a carboxylic acid attached. There are some compounds, obviously, that have common names. Ethanoic acid is vinegar, right? So I just want you to be aware that I'm going to not be testing you guys on IUPAC naming of carboxylic acids, but that's pretty much the long and short of it. Properties of carboxylic acid. So let's talk a little bit about its acidity. The proton on the oxygen is the most acidic proton. So if you think about rationalizing this using stuff we already know, we know that if I added a base and I grabbed the proton, breaking the bond in acid-base chemistry, the negative charge left behind is pretty stable. How do we know this? Well, because the negative charge left behind, I can use REO to determine its relative stability. What atom is it? Well, it's an oxygen. Oxygens are fairly electronegative, so that's boding well. We have resonance, right? I can draw resonance structures to distribute and delocalize that negative charge across three atoms so that the negative charge can be distributed in two ways. Across two different O minuses. So that's great. That largely enhances the stability of the conjugate base anion. So there we are, right? We have a pretty stable negative charge, so it's a pretty decent acid. And as a result, we see that the pKa for carboxylic acids are around 4 to 5. What's the pKa for water? Just to put it into perspective, you guys remember? 15.7. Also, interestingly, carboxylic acids, volatile ones, are typically the ones that are responsible for bad odors. So our sweat, rancid meats and milk, and it's exactly why, you know, your mom wants you to put baking soda in your refrigerator so that it neutralizes all of those nasty carboxylic acids getting generated. Sodium bicarbonate is what baking soda is. It's a weak base. And so that is going to just do some acid-base chemistry to neutralize those smells. That's why you see, if you've ever wondered why Arm & Hammer looks like they're putting baking soda in everything from toothpaste to deodorant to, right, just selling baking soda as a freshener for your refrigerator, it is indeed doing some acid-base chemistry. I've listed 2 molecules here that are responsible for the smell of sweat, and I'll talk about those in a minute. But before we go forward, I just want to point out too, from an acidity standpoint, that the pKa, if you have a dioic acid, and this, again, thinking about REO shouldn't be a big surprise. If you have a dioic acid with the other carboxylic acid in close proximity, what you'll find is that the pKa for the first deprotonation is actually a lot more acidic. It's a lot lower. Why is that? Well, if you deprotonate it, what do you get? Because that's how we analyze acid-base chemistry, right? The A tells me I've got an oxygen. Well, I saw that before, and the pKa above said it was 4 to 5. Why is it 2.8? Well, we've got resonance, right? You can say, well, we had that above. You just showed me I had resonance, and the pKa was 4 to 5. Well, given what we just covered in the last chapters, do we or do we not have an electron withdrawing group? Carbonyls are electron withdrawing groups, and we do have a negative charge. Negative charges are stabilized by electron withdrawing groups, positive charges are stabilized by electron donating groups. So by induction, things are looking even brighter. Therefore, the negative charge is even more stabilized in this dioic acid than it was with just one of the acids present, because now I've added an electron withdrawing group. So I just think that's kind of interesting given what we just talked about in the aromatic chapter and the Diels-Alder chapter with trying to define electron donating and electron withdrawing groups. Here's a cool schematic for body odor, bad breath, foot odor, flatulence even. You can see through the smell of sweat, I show the 2 carboxylic acids that are present. And these are generated from bacteria that are causing these compounds to be made. You can see that there's 2 carboxylic acids, much smaller, more volatile carboxylic acids for foot odor. And you can see that it's actually more sulfur-based when it comes out of one end or the other. Interestingly, you can take these molecules from sweat, from underarm sweat, and start thinking about chemistry that we have learned in this course and ask yourself if the bacteria makes one or the other and how they're interconverted. So I just want to do this chemistry with you because it's a nice review and it really shows you that you guys have so much under your belt that allows you to really think about the chemistry. So if we started with A and we're looking to form B, you'll notice that all the chemistry is happening across, well, let's number them, 1, 2, 3. All the chemistry is happening across carbons 2 and 3. 2 and 3 starts as a double bond and it's changing into something else. So your brain thinks functionality-wise, all right, it's a double bond and it's gonna not be a double bond. So this is putting me from last chapter into the alkene reaction chemistry. And you'll notice that the new things that are added is an OH and another H. There was already one H there. Now there's 2. So we've effectively hydrolyzed the molecule. We've added water across the molecule. The way that we did this in the alkene chapter was by having it in acidic conditions. Oh, look, we're already in acidic conditions. We have a carboxylic acid. Let me just make this equilibrium, acidic conditions, and, water, because it's sweat and you're probably got water present, and that's what it looks like I'm adding anyway. So let's just use our old pi base chemistry. Make the pi bond act like the base and open up and attack an acid that's already around, hanging around in solution, maybe another sweat molecule. Now the pi bond, when it adds the hydrogen, I'm going to put the new hydrogen at carbon 2, and I'm going to create a tertiary carbocation because that's what we would have done. We wanted to form the more stable carbocation. It's tertiary. I also don't want to put it at carbon 2 because carbon 2 is right next to an electron withdrawing group. You can't withdraw from a hole, so definitely the best position was carbon 3. At this point, we're going to just continue like it's SN1. We have a weak nucleophile, water, and it attacks carbon 3. Putting the OH at the Markovnikov position, and then we're ready for workup. And through chemistry that we have learned, we know how sweat can convert one of its molecules, or whether it's our body or the bacteria can convert one of the molecules into the other. How about the other way around? What if we started with B and formed A? Let's see if we can do that. This is all good electron pushing practice. Starting with B. Now, if I start with B and I look to making A, I notice that A has a new pi bond. How do we know how to make new pi bonds? The answer's elimination. And since we are under acidic conditions, because we have carboxylic acids as part of the molecule, right? We can protonate our OH. And if that's the case, this is helping us to determine which elimination am I shooting for? I'm under acidic conditions, probably got water everywhere. I have a tertiary leaving group. I'm probably going to do E1. The leaving group is going to leave. I'm going to form a tertiary carbocation. Oh, look, that's what I was. I'm literally just going backwards from the reaction we just did. The next step would be water attacking as my weak nucleophile. Sorry, as my weak base. And I grab the alpha position proton. I could have gone for the other hydrogen on the other side. But why didn't I? Why is this the major product, A? Why didn't I not see this guy over here on the left? I mean, the double bond is tri-substituted, right? It's also tri-substituted here. Given what you guys learned in previous chapters, very recent chapters, exam 2 material, what tells us about stability between A, which is the product we see, and the other one, which we don't see? Figured it out? A is conjugated. Look at the pi system. Those pi bonds are conjugated to one another and thus have resonance and really, really, really stabilize the molecule. The energy level is drastically different between these two compounds, thus favoring A.